Fine.
The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody, and welcome to this morning's seminar on Persulfate, the Regenesis Activated Persulfate project. My name is Dr. Jeremy Bernstein-Dingle. I'm Managing Director of Regenesis in Europe. This morning's webinar is actually a recording of one which was presented in the United States recently, although at a time of day that most of us good folks in Europe were doing things other than working, such as sleeping or working late. The other value, I think, in this particular broadcast is that it gives us the opportunity to hear from the original speakers, namely Dr. Ben Mork, who's the head of R&D in Regenesis, and a gentleman by the name of Rick McGregor from In Situ Technologies up in Canada, who talks for the most part of the presentation about his field work with the new product Persulfate and his comparison with other forms of activated Persulfate in the field. In short, the principal development that this presentation will be dealing with is that Persulfate is a catalyzed rather than an activated form of the in situ chemical oxidant based around Persulfate. And the relevance of this is that a catalyst, unlike an activator, is not consumed in the reaction itself. The value of that is that no additional reagents need to be added, so the material comes as a one-part product. Smaller volumes are required. The field work becomes simpler and safer, and the performance becomes much more effective. So these are the points of theory behind it and the ideas behind developing the product. But now we'll move on to the seminar proper. So some of the science behind it can be described by Dr. Mork, and then the actual fieldwork practicality and performance and comparative performance is then presented by an independent contractor, Rick McGregor. Please do take the opportunity to type any questions that you might have as the webinar proceeds. We will collate these at the end, but more of this will be discussed in the actual taped introduction presented to the webinar, which we will start directly. Many thanks.
Okay, well, I'd like to welcome everybody today. My name is Brian Vigue, and I head up the marketing efforts here at Regenesis. And I'll be your host, kind of running the webinar from behind the scenes here. And before we begin, we have just a few administrative items to cover. If you've been to one of our webinars before, you probably heard these, but it's good for the group that may not have been. So as we're limited to just about an hour, and for efficiency, this presentation will be conducted with the microphone settings on mute, so there's virtually no communication between verbal communication during the webinar. And really this is intended just to minimize interruptions and any background noise that may be experienced during the webcast. And more importantly, if you have questions, we encourage you to submit those questions using the online chat questions feature, which is located on your interface. We plan to answer some of these questions toward the end, and depending on how much time we have, we typically get a lot of questions, so we typically wind up answering some of those via email. But please feel free to ask your questions using the online chat. And as an aside, if the webinar or the audio quality degrades for some reason, the audio or the visual, we recommend you please disconnect and repeat the original login steps to rejoin the webcast. And a little bit about Regenesis, if you're not familiar with the company. For close to 20 years now, Regenesis has been dedicated to the development, manufacturing, and supply of groundwater and soil remediation reagents to environmental consulting firms around the world. And we offer a range of proven and cost-effective technologies for in-situ chemical oxidation, enhanced aerobic and anaerobic bioremediation, bioaugmentation, in-situ chemical reduction, and metals mobilization. I could go on with some of the other capabilities we have, but in the interest of time, if you have any other questions about Regenesis, please visit regenesis.com. So that leads us into our presentation for today. And today we're pleased to bring you a webcast on in-situ chemical oxidation and the comparative use of two different types of persulfate-based products. The content is focused on 2 petroleum-impacted remediation field studies that were designed to evaluate the effectiveness of catalyzed persulfate, or Persulfox, or versus base-activated persulfate. Now, to walk us through the information and the field studies, we are excited to have a great guest speaker with us. And I'd like to welcome Rick McGregor of In Situ Remediation Services. Welcome, Rick. Rick is the project manager in charge of both the field studies that will be discussed today. So he's going to go into some details about findings and applications and what have you. And so just a little bit about Rick's background to get you up to speed. Rick is the president of In Situ Remediation Services based in Southern Ontario, Canada. Rick holds a Bachelor of Science and Master's of Science from the University of Waterloo in hydrogeology and geochemistry, and has over 20 years experience in situ remediation. His additional experience includes working as a research hydrogeologist with Environment Canada's Wastewater Technology Center, as well as leading a mid-sized consultants remediation group. His company specializes in the design and delivery of various chemical and biological reagents to the subsurface with sites across Canada and internationally. He's also served on numerous Canadian and American federal government technical committees and has published several peer-reviewed papers on assessment and remediation. So with that, at this point, we thought it would be pretty valuable to have a brief recap of Persulfox, or catalyzed persulfate. And so to give us a short review of this relatively new technology, or new persulfate-based product, we have Dr. Ben Mork with us, who's the Vice President of Research and Development at Regenesis. At this point, I'm going to hand it over to Ben, and then we'll get into Rick's section afterwards. Ben, over to you.
Thank you, Brian, and thank everyone for joining us today. Before we let Rick get started with his talk, I just wanted to take a minute to give a brief background and then intro to our technology, as Brian mentioned. The main feature of the studies that will be discussed today is in situ chemical oxidation. And for those who may not have attended some of our past webinars or may not be familiar more specifically with these remediation technologies, I'll be brief because most probably are. In situ chemical oxidation, or ISCO, is used for remediation of contaminated soil and ground. And it can be used to treat, depending on the reagent and the conditions, a wide variety of contaminants, hydrocarbons, fuels, and other materials, fluorinated compounds, including solvents, and oxygenates like MTB and dioxane. Typically, the oxidants are injected or mixed into groundwater and soil, and it's a mass removal type of a technology. So you're removing a significant chunk of contamination or fraction of contamination with each application. Fairly fast-acting compared to some other approaches. It's done in situ in large part in many cases, which allows relatively efficient, low-cost site cleanup. So application of oxygen to destroy contaminants, up to thousands of ppm in soil and groundwater. That's just kind of a general demarcation, but typically not used for large quantities of pre-phase contaminant, which can be removed by other means first. Figure out how to advance the slide here. There we go. I think there was a delay. So Regenesis has a platform technology for catalyzing or enhancing in situ chemical oxidation reactions. It applies across a variety of different oxidants, including sodium percarbonate, which is the basis for our Regenox product line. We now have a sodium persulfate-based product line called Persulfox, which will be part of the topic discussed today. The surface-mediated oxidation is essentially a heterogeneous catalyst. I hope you can see the mouse cursor here sort of scrolling over what is a computer model of a silica surface, featuring a sort of absorptive interaction with a persulfate anion and a benzene molecule, which is this six-membered black six-membered ring. The silica surface essentially functions to absorb contaminants and oxidizing species, to facilitate radical or direct oxidation reactions, and ultimately accelerate or enhance the oxidation of contaminants efficiency-wise, make it faster and more efficient. Just generally, sodium persulfate is a fairly attractive ISCO agent. The formula is Na2S2O8, and the cartoon on the right is, again, a computer-generated model of sulfur S2O8 of dianion, and yellow representing sulfur, and red representing oxygen. You can see the oxygen-oxygen bond here in the middle, which is the source of the oxidizing capacity. The material has an active oxygen of about 6.7% by weight, and favorable properties for use in ISCO. It's stable for storage and transport. The colorless crystalline solid, very soluble in water with a strong oxidizer at approximately 2.1 electron volts. So it's been around for a while, and there's a number of technologies you can use to activate sodium persulfate for environmental remediation. These include chelated metals, such as iron EDTA. Heat is a very effective way to activate persulfate. Hydrogen peroxide, or base or alkaline activation, whereby you raise the pH of the aquifer above 10 or oftentimes 11, as a target pH. Now, each of these methodologies have been well studied and known to have certain attributes and benefits and disadvantages. Some of the limitations we've defined as we brought our surface-mediated technology to market are with chelated metals. You have a limited range of efficacy, so it doesn't treat certain contaminants like hydrocarbons and chlorinated ethane. Heat, although very chemically effective, can be complex or costly to implement in a site for raising the temperature of soil and groundwater significantly. It can be difficult or costly. Hydrogen peroxide presents similar issues as implementing Fenton's chemistry, which is you have heat and pressure generated on site, and you have the handling, health and safety issues associated with handling hydrogen peroxide. The hydrogen peroxide also has fairly short lifetime in situ, on the order of a couple days or even less. Lastly, caustic or base or alkaline activation is commonly used, quite effective across a broad range of contaminants. Although it does require handling typically 25% sodium hydroxide or caustic, so that can cause skin burns and have some health and safety considerations associated with it. Also, in base activation, the pH of the aquifer must be maintained at a high level to continue to activate the persulfate. So acids that are generated in oxidation reactions or buffering by the aquifer can drop that pH out of the target zone and can result in sort of a decreased or deactivation. So just lastly, to wrap up my short section here, we have a product now called Persulfate in the marketplace, which is based on Regenesis surface-mediated oxidation technology. It's an all-in-one material shown here in the picture on the right, such that it is a soluble powder. You just mix it directly in water and stir it and inject it into the subsurface or mix it in, however the application is designed. Treats a wide range of contaminants. We have lots of lab data on the common classes of contaminants, chlorinated solvents, hydrocarbons, and oxygenates like MTB and dioxane. We're also getting some great field data emerging, such as some of what Rick will talk about today as an example. And it's very safe. It's relatively very safe and easy to use. Of course, it's still a chemical reagent. It needs to be handled according to MSDS and recommended safety procedures. But in contrast to some of the other activation technologies, it has some favorable attributes in that manner. So with that, I don't want to take too long out of the talk today. I want to thank you all for joining us, and I do want to turn it over to Rick McGregor. So we're looking forward to hearing his talk today. And Rick, I'll turn it over to you.
Thank you, Ben. So I'll get right into the field studies that we did. We did 2 field studies in southern Ontario. One was done on an overburn site, a glacial till type site, and the other one was done on a fractured rock site up in eastern Ontario. Initially, both of these sites were addressed with sodium hydroxide activated persulfate. However, over time, the treatment objectives weren't being met. So we decided to do a study where we tried the new product, the Catalyzed persulfate or Persulfate. And while we did these studies, we were looking at 4 different things. One was how did it go into the ground, or the distribution evaluation, both vertically and laterally. We also wanted to look at delivery issues. Were there any issues with either of the reagents? Then, more importantly, we're looking at the persistence of both the reagents within the 2 different geologic environments, as well as potential rebound reactions. So, as I said earlier, the 2 sites were both in Ontario. One was in southwestern Ontario, down near Detroit. It was an overburden, so we had a glacial overburden. And then in the eastern Ontario site, it was in a fractured rock, basically a fractured limestone with a fairly high porosity. At the first overburden site, the contaminant we're looking at was a gasoline plume off of a former gas station. At the fractured rock site, it was a fuel oil impacted aquifer that we were treating. So as I sort of suggested earlier, we addressed both of these sites initially with sodium hydroxide activated persulfate. It was done in multiple injections, either between 3 or 4 injections were done at each site. While we did see fairly good treatment of both the gasoline and fuel oil impacts, the objectives at each site were not met, and that was over about a 2-year period. So it was at that point we decided to try a different approach, and that's where we brought in the Persulfate. The main issue it appeared at these sites was that we were not maintaining high enough pH. As sort of Ben suggested earlier, the pH for base activated persulfate needs to be of 10 to 11 for that activation to take place. At both sites, you'll see with the data we show later on that our pH was only elevated at those 2 sites for maybe 2 to 3 days at most, and then the pH dropped down to and eventually reached background concentrations. So one of the sites we think that's related to is just due to our natural high carbonate content within our aquifers. So at the overburden site, we had about 2 to 3 weight percent calcium carbonate within soil, whereupon the fractured rock site itself was a limestone-based aquifer. So this is just a brief overview of the 2 sites. So the overburden site on the left of your screen, the geology was a silty sand with interbedded layers of sand, silt, and clay, so it's quite heterogeneous. Our hydraulic activity varied from about 10 to -4 to 10 to -6. The plume itself extended to about 100 feet in length and about a meter or 3 feet thick, and about 20 feet wide. So it's a fairly small plume. The hydrogeology consisted of the aquifer itself with an unconfined aquifer with a water table about 2 meters below ground surface. We did see seasonal fluctuations with the water table over the year of about half a meter, or about a foot and a half. The aquifer prior to treatment was anaerobic in geochemistry as well as the sulfate reducing. The contaminants of concern were mostly BTEX with what we call the F1, F2 portions, so your gasoline range contaminants. Prior to any remediation happening in the solvent plume, our concentrations were up to 80 milligrams per liter. So we did have some NAPL present in the form of fine sheet, maybe less than a centimeter thick sheet. Second site, we had fractured rock. It was a fractured limestone with a high porosity. So you'll see data once we get into matrix diffusion data. We'll show later. You'll see how come that's important. Once again, it was an unconfined aquifer with the water table fairly shallow, 1.5 meters below ground or 5 feet. Its fluctuations were about a foot a year, so it wasn't as much as the other overburden site. Bulk hydraulic conductivity is 10 to -6 meters per second, with the aquifer being anaerobic and iron reducing prior to remediation. The contaminants of concern here were nil heavier than at the overburden site, with our F2, F3 being the most being the compounds most of concern here, with our starting concentration of about 45 milligrams per liter. So once again, we did have sheen present on the water prior to remediation. For those out there who are interested in the SOD or the NODs, we didn't do those at the fracture site, but at the overburden site we did do a fair bit, and we had an average mean SOD of 2.3 grams per kilogram with a range of about 1.9 to 3.2 grams per kilogram. So the SOD, NOD were fairly low, probably typical of what we would see in southern Ontario for this type of geologic material. So this is a schematic of the first site, the overburden site, showing the plume that's coming off the tank, former tank nest, consistent of BTEX F1, F2. On your right of your screen, you'll see a simplified geologic cross column here. And basically our zone of impact were about 1.5 meters thick, with the smear zone being about 0.5 meter and the sulfate plume being about 1 meter below the water table. So initially, we started the site out using the sodium hydroxide persulfate injections. We did 4 injections over a 2-year period. And as I said earlier, we did not see the remedial objectives met for the site. So it was decided to continue on with the sodium hydroxide persulfate injections on the southern part of the plume in this half. And then on the northern half of the plume, we decided to inject Persulfate. And the idea was to see if we could do a direct comparison of the performance of the 2 reagents over time. So this is sort of the overview of the program. In the source area where the tanks were, there was a separate program done for the removal of any NAPL that was present, as well as the remaining dissolved phase was addressed with absorption media. We won't talk about that today. We'll talk more about the plume program, which consisted of the chemical oxidation consisting of sodium hydroxide activated persulfate as well as persulfate. Once we got down to certain levels, we were going to polish the remaining plume using aerobic bioremediation using compounds such as ORC. The reagents themselves were delivered. The design of the program was based on work done by Crims et al. That showed that once you inject about half the pore volume within the aquifer, you had a much better probability of success of remaining in the aquifer. So that was part of the design program, was to inject at least half the pore volume of reagent within the aquifer. This was done over multiple events. For the sodium hydroxide, prior to the application of Persulfate, we injected 4 events. After we started doing the comparison injection, we injected 2. There was 2 injections of each compound in each half of the plume. The reagents were delivered using direct push technology, equipped with horizontal tools. They were done at multiple injections, so we used about a 2 meter by 2 meter grid to inject this, and they were done at multiple intervals. And by that I mean they were not just done at 1 depth, they were done at 2 or 3 depths throughout the plume. We delivered the reagents at very low pressure. We usually try to go below 10 psi, but in some cases we did get up to about 22 psi. And each injection point was, or location was injected with a fairly low volume, about 50 gallons per location. So as I said earlier, one of the things we're interested in is the distribution of the 2 reagents once we went in the ground. So these, what we did was, after we did the injection, we came back a few hours later and we did cores throughout the area of injection. So these plots show the areal extent of the 2 reagents. On the left, your base-activated persulfate. On your right is your persulfate. And what we did was take soil cores every half meter surrounding the point of injection, and then we took samples every 20 centimeters throughout the depth of that core. And what we're looking for is the presence of, in the case of the base-activated sulfate, we're doing pH measurements on the pore water within the soil. And on the case of the persulfate, we're looking for the catalyst itself. So these plots just show what we found basically 4 hours after we did the injection. You'll see both the distributions are fairly similar, so we didn't see much difference in how the distribution happened with both oxidants. The persulfate, based on our mass balance, was slightly larger than the base-activated persulfate, but probably not within the limits of the calculation. So at the end of the day, we concluded that we got both good distribution with both reagents. As you can see here, the reagent scales are in meters, so we've seen about a 3 by 3 meter, if you want to call it, area of influence around each injection point, and they're fairly uniform, which was a bit surprising, but in this case, that's good. So the next thing we want to know is how long do these reagents last in the ground? As I said earlier, the reason we were doing these studies was we were finding the base-activated persulfate, the pH of the groundwater was not staying above pH 10 to 11 for a very long time. So we're wondering about the cause and if we can address that cause. So when we looked at persulfate persistence, this just shows 1 day after the injection versus 4 days after the injection. And once again, we took cores of the soil to look at the concentration within the pore water itself. As you can see here, we did see a decrease in the catalyst present for the persulfate. We've seen about a 25% decrease in the mass of catalyst present within the soil after about 4 days. When we looked at the pH of the pore water, and this was for the base-activated persulfate, we've seen after 4 days, basically the pH was only above the 10 to 11 in a couple of the soil samples, suggesting that basically the activation process was finished before 4 days was done. So that was in the aerial view. We want to also look at vertical. And this slide just shows the vertical profile of the Persulfate and how long it was present within the soil column. So we have here is three data points, one for 4 hours after injection, one for 1 day, and one for 4 days. We also collected later on data, but I just limited to this today. So we want to first see is when we injected using direct push, did we actually get the oxygen within the target zone? And you can see by this graph that, yes, we're very successful in that point in getting the oxygen within the target zone. So that was number one injector was done. The second thing is the oxygen, in this case Persulfate, persists within the ground. And we can see about 20% of it was consumed after about 4 days. But still, we had 80% remaining after 4 days, which was very good. When we did a pH of the groundwater sample from wells within the area of injection, we just looked at here, we looked at over 3 weeks the pH of the pore water, and this is for the base activated Persulfate. And we see here that basically we want to keep the pH above 10 to 11 to keep this Persulfate activated. As you can see here, after about 2 to 3 days, our pH dropped to below the pH 10, which means it's generally not going to be that effective on an activated point of view. This is a vertical profile, once again, for the base activated Persulfate. And we see similar plot. Originally, we were very successful in injecting the Persulfate within the target zone itself, but when we look at the persistence of the pH or the high pH conditions within the pore water, we see that it decreased quite quickly over about a 2 to 3 day period and dropped below pH 10 by the 4 day period here. So treatment of this, I guess most people are probably interested did that actually work. So when we look at the BTEX compounds here, this graph's now confused, so hang in there with me. This part of the graph just shows prior to any injections being done. So you can see we're between 80 and basically almost 100 milligrams per liter within the pore water of BTEX. After that, this point here, that's when the base activated Persulfate injections started. I mean, over this period of time, we had 4 injections. Sorry, between this period here, we had 4 injection periods. And initially, we've seen a very good decrease. We've seen almost a 70 to 80% decrease in the BTEX concentration. And then we see some rebound, which was expected, and then we've seen our decrease. But then we kept seeing this rebound reaction happening. And we kind of settled out between about 30 and 40 milligrams per liter, which, well, a significant reduction over the original results, was not anywhere near the remedial injections of the cycle. So what we did last fall was we divided that plume into half, like I showed in the figure prior to this. And at half the plume, we injected Persulfate, and the base activated Persulfate, and the other half the plume we injected Persulfate. And these are basically, well, we can't say these wells are exactly the same. These are basically the average concentrations within the wells, within the plume that we injected. As you see, the Persulfate, we've seen a bit of a reduction, about a 25% reduction over the 2 injection interval periods that we did. However, for the Persulfate, we've seen a dramatic decrease down to basically detection limits within 1 injection. We had to actually complete 1 injection of Persulfate, and we monitored since we haven't seen any rebound yet in the Persulfate. When we look at the F2 fraction, so the nil heavier fraction here, one of the things you first see at this graph is that we actually, at the start, we had no F2. So the question is why are we getting F2 now? And one of the answers to that might be is because we're basically oxidizing the absorbed media that the F2 would be absorbed on, and that would come off. I don't think that's the case at this site. I think this case is we've just seen the F2 is retarded relative to the BTEX F1 compounds, and this is just a late, we want to call breakthrough into the wells that are down there. If you remember, this plume is very small, and it's a fairly fresh spill, so we're just seeing a delayed response in the F2 transport actually at the site. So initially, we, as you can see here, during the first base activated Persulfate injection, we actually did not actually see any treatment at all at the F2 fraction, which was a bit surprising. Now that may just be because it was all the sulfate was being consumed by the F1 and BTEX, but in any event, we did not see any treatment of the F2 during this period. Once we switched into the comparison study of the Persulfate, base activated Persulfate, which is the blue graph, and the Persulfox, which is the red graph, we once again see similar results that we've seen in the BTEX F1 fractions, where we see some treatment, about 20% treatment for the F2, but we see a more dramatic treatment for the F2, the Persulfox itself. So an overview of the site 1 for the distribution. Three things we're really concerned about is distribution. We've seen similar distribution patterns both vertically and laterally for both the base activated Persulfate and the Persulfox. And based on our experience, their distribution is very good compared to other oxidants such as hydrogen peroxide that we've used in the past. The persistence at this site, the base activated Persulfate, the pH basically decreased below that the key number of 10 to 11 after 3 to 4 days, suggesting that activation may not be occurring after that point. After 4 days, we did see at least 75% of the Persulfox catalyst still present, which suggested to us that we were still going to get further reactions. Treatment-wise, they both were very effective at treating the BTEX F1 portions of the plume. However, the base activated Persulfate did seem to reach a plateau and did seem to suffer from rebound issues, whereupon the Persulfox currently does not seem to have as much rebound issues as the base activated Persulfate. We'll get into reasons why we think that is a bit later in the talk. So I'll move on to the second site here. It was a fractured rock site. And at this site, similar type of approach as we did at the Overburn site, where we had a source removal program for the NAPL, which involved excavation, as well as basically bailing of vein-free product. Once that was done, a chemical oxidation program was implemented, followed by aerobic bioremediation to polish the remaining hydrocarbons. This site, though, is slightly different in the approach of the comparison study, where we just at the start did base activated Persulfate, and then once we realized we weren't meeting the remedial objectives, we switched over to Persulfox to try to finish off the site. Being fractured rock, we could not inject using direct push, so we had to inject into using injection wells installed within the fractured rock. Some of the wells were packed off to allow us to inject directly into the fractures that we were looking at remediating. We're injecting at a relatively low pressure, and once again using low volumes. The volumes here were a bit lower than the Overburn site just because the fractures themselves could only handle so much volume until they were basically, I don't want to exaggerate, but they could not handle anymore. So this is just a graph showing, once again, the persistence of the base activated Persulfate in the surrounding monitoring wells. I want to point out here, we don't use any of the monitoring wells for injection, so none of the data is advised that way. And so this graph just showing, once again, is we're trying to keep the pH here above the 10 to 11 mark. I haven't marked 11 on this graph, but 10 to 11 is kind of the goal here. And as you can see, we stay above 10 for about 3 days, and then afterwards we start to decrease pretty rapidly until we get back down into the base background pH of about 7.1. When we looked at the persistence of the Persulfox, and the way we measured this was by looking at the catalyst that was still within the groundwater. We see after about 3 weeks, we've consumed about just less than 20% of the catalyst that's within the groundwater. So we see very good persistence of the Persulfox in this environment. So once we look at the treatment treatment of the compounds of concern here, we once again we're focused on the F2, F3 fractions at this site, being the heating oil. You see we started out about 30,000 micrograms per liter, and then after the first, once we entered the base activated Persulfate injections, which is the zone here, which occurred over about a 2-year period, we see that we see dramatic decreases, but then we start to see these rebound reactions. And then over this period, we've seen 4 injections. I didn't mark on the injections here, but basically one occurred here, 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 and here. We started seeing the rebound again happening. So we switched over to Persulfate. We did one Persulfate injection basically right at this dashed line. And over the 6 to 7 months since that injection, we have seen the concentrations of F2 at these sites. Basically, this is the average of all the wells within the injection area, remaining at or just below detection limit, so well below the cleanup criteria at this site. When we switch over to the F3 fraction, we see very similar results as what we did for the F2. Generally speaking, the heavier chain carbons are more difficult to oxidize and take a longer time. In this case, we've seen a similar response as we did for the F2, suggesting that once again at this site, the Persulfate was able to handle the remaining concentrations, which were about 10 milligrams per liter, and remaining down there. So we didn't see much of the rebound. So why did we see rebound? I borrowed or sold or modified this caption from Cooper and Davies. This was developed for Dean Apple, but the same addresses for these both sites. The L and Apple is basically what you do is have your release, and it goes to the unsaturated zone into the soil or overburden and into the fractured rock. Okay, so you have all the phases present. So what we're really worried about here is the dissolved phase present. What happens here is with the dissolved phase is you'll get the NAPL or the high dissolved mass going into these fractured or highly preferential pathways and then fusing into the big rock matrix or the lower grain or the lower finer grain materials on each side of the entire thing. Now what happens with rebound, for those who, I'm sure most of you know this and that, but is the rebound is after you clean up these high preferential flow pathways fractures, is the contaminants or concerns starts back to fuse out of the fine grain matrix or the rock matrix back into these pathways, and therefore you don't get the cleanup that you were hoping for. So what we try to do to design to try to overcome this is we try to use a very persistent, what we call persistent oxidant or material reagent to flush through these high preferential flow pathways or fractures. And what happens is this then diffuses into the rock matrix or the fine grain materials. And hopefully what you create is basically a reaction pump with the contaminants of concern diffusing outward, your oxidant solution diffusing inwards, and then you have basically a reaction front happening. Hopefully that reaction front is strong enough to overcome the concentrations diffusing out of the rock matrix or the fine grain materials, and it'll hopefully last for a long time. Unfortunately, none of our oxidants last for as long as the contaminants have been around usually, so we're usually fighting an uphill battle, which usually requires multiple injections over a longer period of time. So what we did at the fractured rock site was we went down and we took some cores of the rock itself, and we looked at the concentration of, in the case of the base activated persulfate, we looked at the pH of the pore water within, and remember this is a pretty porous limestone, so we're looking at the pH of the pore water within the limestone matrix itself in this graph on your left. And then in this shaded area here represents the fractures within the rock itself. And then we also did the same thing for the Persulfate, which is on the right side of your screen. And then what we did was we took a core at 14 days and then 28 days after injections, and we looked at how far into the rock matrix itself the basically the Persulfate migrated or diffused, I should say migrate, but diffused into the rock. The idea here was to see if we could create that theoretical reaction front and to see what our concentrations were with time. So as you can see on these two graphs, in which I'll show you, is you get what you expect as time goes on, our diffuser front actually gets bigger. It doesn't really migrate too much more into the rock. You see about the space-activated persulfate made it into about 20 centimeters into the rock, or upon the persulfate made it a bit further, about 24 centimeters based on our measurements. Now, those of who are familiar with diffusion fronts, these are pretty big diffusion fronts for such a short period of time. Once again, I have to point back that we had a very porous rock matrix here. So when we do the comparison of the two side by side after 28 days, you can see that basically after the 28 days we had a higher concentration of persulfox versus the base activated persulfate within our matrix, which suggests that over the longer term we'll have a longer lasting and a more powerful, for lack of a better word, reagent within the rock matrix to combat any back diffusion. So in summary, once again, we've seen, I didn't display the lateral distribution data, but we've seen similar lateral distribution. We couldn't look at vertically because we're in a fractured rock setting, but lateral distribution is very similar within for both reagents. The pH for the base activated persulfate did drop below 10 after about 2 to 3 days, so similar results to the what we've seen at the overburden site. Meanwhile, the persulfox was catalyzed was had been consumed by about 20% after 21 days, so still it was fairly persistent after 3 weeks of application. Treatment, once again, both compounds were very effective on the F2, F3. However, the sodium hydroxide activated persulfate did exhibit some rebound issues and did have, it just didn't seem to be able to reach the final goal. The persulfox itself, to date, and actually I just got back to the latest results today, have shown that we still have not experienced any rebound reactions since the last application, which was about 6 months ago. So that's encouraging, and we're still monitoring the sites for rebound. So overall, for both sites, we can say that the base-activated persulfate and persulfox both showed good treatment of the petroleum hydrocarbons for all the 4 fractions we were looking at. Unfortunately, the base-activated persulfate just could not just meet the regulatory guidelines that we were going for. Lateral distribution and vertical distribution were very good for both sites and very similar. The persulfate persistence seems to be better than the base-activated persulfate, and that's just due to the base we think, being buffered by our high carbonate content aquifers. So maintaining the high pH in our settings in our carbonate aquifers is a real challenge, and we're not quite sure how to overcome that. And then the final thing, which is common to most remedial technologies, is the back diffusion / rebound. There's not much we can do to combat that, but in this case, we are cautiously optimistic that the persulfox seems to have a better or greater diffusion profile compared to base-activated persulfate, which we're hoping will reflect into less rebound over time. But we're still studying. And with that, I guess I'll wrap up, and I guess we can take some questions.
Okay, great. Thanks, Rick. That was very informative. So that concludes kind of the formal presentation section. What I'd like to do now is just offer up a few, sorry, that's what's the computer here. Offer up a few closing items, and then we'll get into the chat questions, just a few administrative things. But please keep in mind, we're continuing to offer these webinars, and we appreciate your feedback. So you'll get a survey, email survey shortly after this, or probably early tomorrow. If you could, please give us your feedback. And it's also a place where you can ask additional questions that might come to your mind after the presentation and what have you. So we'll do every effort, or make every effort to get back to you via email on any questions after in the survey portion. And again, we'll be mailing everybody a formal kind of certificate of completion for this event. And so, granted, we have your proper contact information and what have you. Then we'll have a certificate mailed off to you sometime in the next 10 to 14 days just to document your attendance on the online portion. That can be used in some cases for continuing education units and what have you. And then, so with that, we're going to circle back to the chat questions here. And we've got quite a variety of them on the screen in front of us. So we're going to try to get through most of those here. And then any questions we don't get to, we will follow up with you via email. Because there's, I see probably at least 30, 40, 50 questions here. So with that, I want to go out and start with the first question here. This relates to the sampling density on the aerial extent slide. Maybe if you want to flip back to that slide, Rick, at all, or would that help you kind of go through it at all? Or what the question was, what was the sampling density for evaluating the aerial extent of the contamination, or how many samples? I think you spoke to this, but maybe it just needs to be read.
Yeah, we basically take a core every 50 centimeters, or every half meter laterally, and then when we get to the target zone, we take a core every 20 centimeters, or take a sample, sorry, every 20 centimeters. So over a 5 meter by 5 meter area, you're looking at about, I think we were taking about 70 cores, and then taking from each core, taking about 6 to 7 samples from each core. So we were looking at about 500 to 600 samples per, I guess, per plot here.
That's pretty good resolution.
It is. Sorry, I'm an old Waterloo guy, so I'm sort of used to Waterloo stuff.
This question here is specific to injection pressures.
Yeah.
It's kind of a general question, but why inject at low pressure versus high pressure? Did you have any comments on that?
Yeah, it's you know, there's two schools of thought out there. There's the high pressure and the low pressure school. I'm more of a low pressure guy. I tend to not believe in trying to create preferential pathways if you don't have to. You know, that said, sometimes you do have to do, for lack of a better word, fracking. I know it's a bad word out there right now, but there are some instances of geology where you want to do that. For us, though, for these two sites, we tend to believe we try to put in as low as pressure as we can, and we try to do that to try to mimic natural groundwater flow conditions. And that's the reason we try to do that.
Okay. Here's a question that just kind of came up organically, but can you speak to the differences in the materials as it relates to kind of the handling and the application? You did two different sites here, and is there a difference in handling Persulfate, say, versus the activated Persulfate? What was your experience there?
Yeah, I mean, they're both fairly easy, for lack of a better, easy to inject from an injection point of view. They're fairly liquid. They're not much viscosity, density issues there. And they don't change for us up in Canada. We're always concerned about the changes in the cold, so that's not a big issue. Where we did notice big issues, and Ben sort of discussed it at the start, was from a health and safety point of view. Caustic, anybody's used caustic before probably realized caustic can be very dangerous to use, and it's pretty extreme from the health and safety point of view. So if we can minimize the use of caustic, we try to. From the Persulfate point of view, you just don't have that issue, so you don't have that health and safety concern. So it was, from that point of view, the Persulfate is, I would say, superior from a health and safety point of view than using caustic. The other thing that we always are concerned about is if we get into low permeability environments and we try and do the check and we've mixed up a caustic-based solution and for some reason we can't get it into the ground. What can happen, especially at high caustic concentrations, is you can start to get an exothermic reaction happening when you mix containers, hoses, your injection equipment, which can cause a real problem from a practical point of view. Is what do you do with that solution as it's heating up? So, once again, with Persulfate, you don't have that issue, so that's a big advantage that way.
Okay, great, thank you.
There's another question here about what's F1, F2. F1, I guess, more Canadian type term. F1 is basically your petroleum hydrocarbons within your C6 to C10 range, where F2 is from C10 to C16, I do believe. So are your gas, low-end diesel type ranges. So it's more your lighter-end hydrocarbons.
Okay. So maybe we could go back to this graph. There was a couple questions on the comparison chart with the red and the blue lines. I think that was in the first the overburden site. This might be a good recap for people. The question here just is clarifying, what, maybe you could just rehash this for everybody who's just heard a second.
Yeah, sorry about this. Don't pay attention to the color of the dots. Is probably the simplest thing until this second vertical line here. Prior to this, the whole thing here in this area here, the red dots are the dots that were done on 1/2 plume, and the blue dots are the other half plume. But that doesn't matter until you get to this vertical line. So this part of the graph here just represents pre-treatment by anything. So this is you want to call it the background natural conditions. After this first vertical line, which was in about August 2010, the plume was addressed solely by base-activated Persulfate. So the whole plume was addressed by the injections of the base-activated Persulfate. After the second line, which was in September 2012, that's when the plume was divided in two halves. So the one half was treated with base-activated Persulfate, the blue in this case, in this part, and then the red dots here represent the part of the plume that was addressed with the salt ox. Hopefully that clarifies it.
Yeah, I think that helps. Good. We're kind of looking at the questions, so give us just a minute trying to get through these.
There's a question about the SOD of the site. I sort of went through it at the start. For the fractured rock, we did not do an SOD just because I'm not sure if an SOD is really appropriate for a fractured rock. But for the overburden site, we did do SOD. We did about 7 or 8 SODs for the site. The average SOD was 2.3 grams per kilogram, and the range was about 1.9 to 3.2 grams per kilogram. So it's fairly low SODs, and typical for what we see for silty sand up in our area. We have a very low organic carbon content, so those are pretty typical SODs. Now I want to warn everybody that there's a fair bit of work out there on SODs for persulfate that kind of show that SOD for persulfate may not be as straightforward as an SOD for permanganate. I know Neil Thompson at University of Waterloo did a fair bit of work on that. You probably want to look at his data and his papers to try to understand what the SOD for persulfate is.
And I just noted a couple people were asking SOD, soil oxidant, right?
Yes.
Okay, it's for some people's benefit. That's what it is. So here's one that says at persulfate activated sites, can it be reinjected to reactivate previously injected persulfate?
That's a good question. Actually, there's another question too that I'll combine the two answers. One was how do we increase the pH to about 10 prior to the injection of persulfate? We actually mix the the sodium hydroxide with the persulfate and inject it together. The reason we do that, and this is the answer to the second question, is from a hydrogeology point of view, when you're injecting, you'll be injecting basically you're injecting a slug or a plug of reagent into the groundwater. So that's going to displace the groundwater. So the only way groundwater, I hate to use the term, but mixes within the subsurface is by diffusion and dispersion, which is a very slow and not that efficient of a process. So, and it's definitely a function of your surface area. So if you envision if you're going to inject a slug of persulfate and then follow that up by a slug of sodium hydroxide, the only way those two slugs are going to mix is basically where they contact each other, which is a very inefficient mixing process. So we try to mix those above ground, and hopefully that answers both questions.
Okay. Here's a question about underground infrastructure and facilities with persulfox in comparison to, say, peroxide and Fenton's chemistry. Just the question is there any risk of damage to underground? And yes, it is a persulfate-based material, and so you want to exercise some caution there. And you might want to look at some other reagents, such as Regenox in those situations.
There's a question here on the corrosion of the persulfox. I assume they're talking on the pipes, injection pipes and that. It is a corrosive material, but it's not as aggressive as unactivated persulfate, which can be very aggressive. It's basically an acid. It can, we've had rods not literally dissolve, but the threads basically dissolve within a day of injection. So persulfate by itself is very aggressive. Of course, caustic mixed with persulfate, not as aggressive as persulfate by itself, but it is aggressive. I would say persulfate is probably the least aggressive of those three when it comes down to it. When you're talking about your own equipment, we haven't seen any real issues with the persulfox on our equipment.
So this one is relative to gravity feed injection. I guess in any of these sites, would a gravity feed injection have been acceptable for persulfox? Or?
Yeah, I mean, as I sort of mentioned earlier, we prefer to go in as low as pressure as possible. Gravity feed is always sort of the ultimate. Unfortunately, you have to weigh the cost with waiting around for gravity feed with having people on site and injecting it. So if you can inject it at gravity, then that's great. If you, but generally speaking, you do need a bit of pressure to get it in. So we try to keep it as low as possible.
Great. Well, I think at this point we've answered quite a few questions, and and we're running up against time a little bit here, so I think we're going to conclude, and we'll be going through the rest of the questions and try to get back to you via email on those. Try to touch base with you directly. And again, I think maybe we can advance that slide to the very end slide there, right? If anybody needs to get in touch with you directly, there's some contact information for Rick. Let's get to the very end there. Just take a second. But feel free to reach out. And again, we thank you for attending the Regenesis Remediation webinar series. And please keep an eye on your email for additional webinars to come. Thanks, everybody, and have a great day.
Okay, thank you everybody in Europe for listening to this particular webinar. You'll have heard a number of the US questions, and there'll be plenty more of our own that have been coming in through the course of the webinar. Due to time, we won't be able to answer all of them within the actual broadcast, but we will get back to each of you independently with emails, which should be within the next 48 hours. There'll also be a short survey sent out to you about this. A few questions, though, have come in, and I'm going to clump some of these together as rather than cite them individually. There were several which were asking about methods of injection, how it can be used in different formations, etc. So, for general comment on methods of injection, I'm going to pass over to my colleague Gareth Leonard, who will answer that briefly. Gareth.
Right, thanks, Jeremy. Yes, questions on
the reagent, viscosity of the Persulfate, how it can be injected, and whether the catalyst has any impact on well screen, formation clogging, etc., etc. The answer to that is that the Persulfate product is 100% soluble. The catalyst is based on silicates, which are naturally at a high pH, and so when mixed with water, they are 100% soluble and have a viscosity similar to water. They can therefore be distributed within the formation very effectively, as you saw in some of Rick McGregor's slides. Over time, what then happens is, due to the actual Persulfate reaction dropping the pH, and due to buffering of the formation, the silicates will slowly precipitate out of solution, forming the amorphous silica catalyst itself. So effectively, it's almost moving from a base-activated phase through to the actual catalyst phase. This was touched upon briefly in the talk, but it's actually quite an involved subject. So for those of you who'd be interested in picking up more information on that, I would direct you to the Regenesis website, or indeed a shortcut, www.persulfox.com, persulfox.com, where there'll be more information. It's also possible to download a 16-page technical paper describing how the product works, the methods of activating, the way the catalyst works in the comparison with other approaches. It would also be possible to email any inquiries that you have directly to Regenesis if there are other questions that you have that you've not typed in during the webinar itself. The simplest catch-all email for that I'd recommend to you would simply be europe@regenesis.com. And how are we doing, Callum, with contact? Do we have Gareth online for some of those questions, or are we dead? We'll try again. Okay, we'll try one more time to get over to Gareth for some of the questions on fieldwork, etc. Gareth, are you there?
Hi, am I there? Can you hear me, Jeremy?
watching one of my technical colleagues working through the system like frantic sound engineer. No, unfortunately, we've not been able to get Gareth on a bit of a Today program Radio 4 problem there. But that does bring us to the hour and the end of this particular presentation. So I think at this point we will close off and conclude the seminar. So please, if you have any further questions, do feel free to enter them onto the survey form that will be sent to you, or contact europe@regenesis.com, or indeed cruise the website www.persulfate.com, or indeed the regenesis.com for information. Thank you everybody for attending the webinar, which we now conclude.